My name is Olin Williams, and I'm an architect in the Enterprise Technology Planning Group. We're going to talk about parallel computing using high-performance computing cluster technology. For the update today, we're going through a couple of slides and give you a demo. Today, this technology is in the watch state. Although we have a few niche applications using this technology, it is not in wide use. However, it has great potential for Southern Company as we go forward. HPC technology is all about scaling out instead of scaling up. What do we mean? It means using more processors in parallel rather than single faster processors. Moore's law says that the number of transistors on a chip will double every 18 to 24 months. However, processor speeds have topped out at roughly around 3 gigahertz, and chip manufacturers are now increasing CPU performance by adding multiple cores. For example, Intel's Core 2 Duo, dual and quad core processors. This is parallel computing. Supercomputers, on the other hand, have employed parallel computing for years. What's really interesting is that supercomputer architectures today have evolved to leverage consumer off-the-shelf technologies, or COTS. What this means is that today, supercomputers are not just for research facilities anymore. Here are 4 key dramatic trends identified in the semi-annual Top 500 Supercomputer Survey. First, 72% of the fastest computers in the world are now leveraging cluster architecture. Second, Linux is the preferred operating system for the fastest computers in the world today. Third, Gigabit Ethernet is becoming the network fabric of choice for connecting the nodes of supercomputers. And finally, most supercomputers today use non-proprietary common desktop and server processors from Intel, AMD, and the PowerPC from IBM. Let's take a look at some of the fastest computers in the world. IBM's BlueGene-L at Lawrence Livermore National Labs is currently the fastest computer in the world with over 131,000 processing nodes. The second fastest computer in the world today is Sandia National Labs Red Storm with over 26,000 AMD dual-core processing nodes. The third fastest computer in the world, which I had an opportunity to see firsthand, is the BlueGene-W at the IBM Watson Research Center in New York. It has over 40,000 processing nodes and has the same architecture as the BlueGene-L at Lawrence Livermore. As you move down the top 500 list, we have the 41st fastest computer in the world at Georgia Tech. It is a 1,000 node IBM cluster. Here is Little Phi, whose name is a play on the old term for mainframe computers, Big Iron. It is a portable cluster that fits in a case. It weighs less than 50 pounds and sets up in 10 minutes for training and research. Now let's take a quick look at today's supercomputer architecture. The IBM BlueGene-L architecture begins with 2 dual-core PowerPC chips that are put on a card. These cards are put in a tray, and the trays are stacked on a rack to form the cluster. One rack of the BlueGene supercomputer contains over 2,000 compute nodes. The BlueGene-L at Lawrence Livermore is built using 64 racks and contains over 131,000 compute nodes. Today, high-performance computing clusters can be assembled with off-the-shelf parts. Here's a diagram of a cluster I built at home last year. Its architecture is identical to the supercomputers of the top 500. It's based on Intel-compatible processors, Gigabit Ethernet, and Linux. Here are some pictures of my home-built high-performance computing cluster. There's the host node console, the Gigabit Ethernet switch, and the compute nodes. Here's a photo of a test high-performance computing cluster that we assembled in our ETP technology lab across the hall. It's architected using a 24-node cluster of Dell GX 620s, our desktop computer, Gig Ethernet, and Linux. Just to show you how powerful this configuration is, it produced 68 gigaflops, while our Southern Company mainframe produces about 2 gigaflops. So this cluster conceivably could execute 30 times faster than our mainframe. Here is a consumer, off-the-shelf PC motherboard placed in an inexpensive case to create a high-performance compute node. Here we've connected 12 of these compute nodes together with Gigabit Ethernet to form a test HPC cluster. Southern Company Generation Engineering is using ANSYS CFX to model fluid dynamics and plans to use high-performance computing cluster technology to improve their models. The Southern Company Research and Environmental Group has used cluster technology to perform air quality simulations. They're also planning to use this technology to analyze market data. Also listed here are some of the ones in which parallel computing technology could have an impact in Southern Company in the future. The bold entries are ones that are related to system operations. A very popular use of parallel computing today is in visualization clusters. This is a visualization theater used by Lawrence Livermore to observe data being created by their BlueGene L supercomputer. For example, high-resolution genetic gene folding and simulations of nuclear reactions can be observed and analyzed. High-performance visualization clusters also enable you to have a 3D immersive experience with the data. Here are a couple of screenshots that show the results of two Octave programs. The graph on the left is the kernel density function that provides more information than the classic histogram for statistical data. The one on the right is a calculation and graphical visualization of the Mandelbrot fractal. Fractal sets are used in video compression, antenna design, earthquake modeling, and other areas, as well as attractive screensavers. In this demo, we will be using a high-performance computing cluster created using a live Linux CD developed by Michael Creel, an econometrics professor at the University of Barcelona. With this CD, we can build a cluster in 5 minutes. We'll compile and run parallel applications written in C and Fortran. We'll also run some parallel Octave applications. Octave is a high-level, open-source interpretive language similar to MATLAB, intended for numerical computations. And finally, we'll demonstrate with the cluster high-reliability parallel computing.